Hello everyone, I am Dustin Kern and I will be presenting our work on integrating privacy into the electric vehicle charging architecture. Electric vehicles are generally considered a key point in the development of an environmentally friendly transportation sector, which is why there's been a lot of advocacy for more EV adoption over the past few years. And we can see that, for example, the global number of EVs had already exceeded 60 million last year. EVs not only charge at home, but often also at public charge points. To make this process as user-friendly as possible, several roles for backend systems have been established over the past years, and several communication protocols have also been developed to enable the automatic exchange of information between these actors. Hereby, an important feature is plug and charge, whereby an EV uses locally installed credentials to more automatically authenticate itself at a charge point for charge authorization billing. Now, the respective communication involves a variety of personal data. However, it does not include appropriate privacy considerations. So, for example, a current protocol simply transfers static user IDs together with the location and time of charge sessions, which allows an adversary to create movement profiles or infer consumer habits. For this reason, it is important to consider privacy-preserving alternatives for the existing processes in the e-mobility architecture. First, some background regarding the involved actors and processes, specifically for contract-based plug and charge. Besides the EV and charge point, there are three backend actors. First, the e-mobility service provider, the EMSP, with whom the EV user has a contract for charge authorization and billing. Next, the charge point operator, the CPO, who manages the charge points and communicates with them for things like load balancing and metering. And finally, the contract clearinghouse, which serves as a roaming platform between several EMSPs and CPOs in order to enable, based on roaming contract, charging at charge points that are not operated by the user's EMSP. Now, regarding the processes, we start with contract credential installation. For this, an EV comes pre-installed with a provisional credential from its manufacturer, which uniquely identifies this vehicle and is provided by the EV user to their EMSP during the conclusion of a charging contract. Now, after the EV is connected to a charge point, it can send a request for contract credentials. This request contains provisional credentials and is forwarded via the backend actors to the EMSP, who responds via the reverse path with contract credentials, which uniquely identify contracts between user and EMSP. Afterwards, the EV can authenticate itself at a charge point via Write and Charge, based on a challenge response protocol using the received contract credentials. Additionally, the charge point verifies that the EV is authorized to charge by sending a request via the backend to the EMSP, which includes the user's contract identifier and the charge location. Now, during a charge session, the charge point periodically queries its electricity meter and can optionally request a signature over the measured values from the EV called metering receipts. Finally, after the charge session is complete, the charge point reports all billing relevant data to its CPO, who forwards this data to the EMSP. This data then includes the user's contract identifier and the charge location, as well as transaction information, which means things like the time and duration of charge, the consumed energy, the applicable tariffs, and so on. For the identification of security and privacy requirements, we analyzed the EV charging system model for threats, considering three different adversaries with relevance for EV charging. First, a network hacker, meaning a $YAO adversary with full control over the network, who cannot break the cryptographic primitives. Second, a local adversary who can physically tamper with EVs and charge points and extract and modify any stored data on the system unless it is tamper protected. And third, we consider honest but curious operators who do not deviate from the defined protocol, but attempt to learn as much information as possible from legitimately received messages. Resulting security threats mainly concern the spoofing of EV users, as their credentials are insufficiently protected from a local adversary, and resulting privacy threats mainly show that every backend actor receives enough linkable data, like long-term pseudonyms or charge locations, to build detailed movement profiles of EV users. In order to address the resulting threats, we propose an extension for plug and charge protocols to enable privacy-preserving charge authorization and billing that remains compatible with the general procedures and data flows of current EV charger protocols to enable an easy integration. The basic idea is to use a trusted platform module, so a TPM 2.0, in the EV as a hardware security module for secure credential storage and usage. Additionally, the EV's signatures are replaced with anonymous signatures based on direct anonymous attestation, DAA, and instead of using the EV's contract ID for charge authorization and billing, we generate tokens based on HMAC that are unlinkable by anyone but the EMSP. Starting with credential installation, for which the EV's provisional credentials are now stored in the EV's TPM. First, the EV generates a DAA key pair in its TPM. Afterwards, the EV can send an encrypted credential request, including the public DAA key and a signature based on the provisional credentials. After receiving the request, an EMSP can verify the data and generate a DAA contract credential based on the received public key. Additionally, the EMSP generates a symmetric key for the generation of authorization tokens and encrypts the created data for the EV's TPM. Now for charge authorization, the EV starts by generating a new session key pair in its TPM. Afterwards, the EV assigns the public session key with its DAA key, so it's an unlinkable DAA signature, and generates an authorization token with its symmetric key that can only be linked by the EMSP for billing purposes. The generated data is sent to the charge point, which can verify the DAA signature based on the EMSP's public key. Additionally, the charge authorization status can be verified by request to the EMSP, including the received token. If all verifications pass, the EV is cleared to charge and can use the session key for any signatures during the charge session, like signing meter receipts, and to secure the binding between EV user authorization and billing data. For the billing of the charge session, the CPO is still informed about the user's consumption and the user's EMSP. Thus, the CPO can still bill the EMSP for the user's consumed energy. The EMSP, on the other hand, is informed about the user's consumption and can identify a user based on the used authorization data, which means that an EMSP is still able to bill its users for their charging sessions, but none of the actors can link any long-term identity of the user to a location anymore. Now, to evaluate the proposed extension with regard to practical and usability aspects, we implemented it as a proof of concept using Raspberry Pis for EV and charge points, connected via powerline communication. The EV was equipped with a hardware TPM, and the charge point communicated via its wireless uplink with the backend, which was implemented as separate virtual machines on PC. Results show that the extension only adds relatively low amounts of communication and computational overhead when compared to a reference implementation, and it shows that the extension remains within the timing and size constraints of existing standards. Additionally, it shows that the extension can be integrated into existing standards with only minor changes, since it is compatible with existing roles and data flows. Moreover, it shows that the extension still supports existing features that go beyond the basic authorization billing processes like meter receipts, charge point reservations, credential installation with certificate pools, and so on. Now, in order to evaluate the security and privacy of our extension, we used the Tamarin Prover, which is a tool for automated symbolic protocol verification. In Xamarin, a protocol is modeled as a set of rules that basically define all communication and data processing steps. Additionally, you can define your security requirements as trace properties that should hold for all possible execution traces of the model. Now, to verify these properties, Xamarin starts with a state where the property has been violated and performs a backward search over the possible rule executions to determine whether there is a valid path that leads to the state. The output is either a counterexample, so an execution path that violates the property, or else a proof that a violation of the property would also contradict the model, which means that the property holds. Analysis is performed in the symbolic model, whereby the adversary has complete control over the network and cryptographic primitives are assumed to be perfectly secure. For the verification of the security requirements, we assume that the backend communication is done by a secure channel, for example via TLS, which is the case in current protocols. However, the adversary has complete control over the charge point's communication in order to model a local adversary that has tampered with the charge point. With regard to security requirements, we mainly verify authentication properties based on the commonly used notion of injective agreements. So we verify injective agreements regarding credential installation, charge authorization, and billing data. On the example of authorization, this means that whenever an EMSP authorizes a charge session, which was apparently initiated by a specific EV, then we know that this EV has requested the authorization and both actors agree on the contained data, and each granted authorization corresponds to a unique request. Now, with regards to privacy requirements, we mainly focus on unlinkability properties using Tamarins observational equivalence model, whereby we show that the adversary cannot decide whether two protocol runs, meaning credential installations, charge authorizations, or billing, were initiated by the same EV or by two different EVs. As mentioned before, the only exception is the US EMSP for billing purposes, where we show that the EMSP is not able to create movement profiles of their users by verifying unlinkability between users and locations, which is verified by showing that they cannot decide whether two charges of an EV were done at either the same charge points or different charge points. In conclusion, I would say that while privacy is important for the charging architecture, it is currently not appropriately considered by related protocols, and a lot of personal data is unnecessarily revealed to a variety of actors. To address this issue, we proposed a privacy-preserving extension for charge authorization and billing based on a detailed security and privacy analysis. Our practical evaluation shows that the extension can be integrated into existing protocols with only minor changes and small overheads, while maintaining compatibility with existing roles and processes. Additionally, we provide symbolic proofs to show that these desired security and privacy properties are fulfilled. And with that, I would like to thank you for your attention.